Okay, so I hope I'm audible. So, welcome back to the weekly tutorial sessions on weak mobile robots. So, for this week, we will be covering the topics, mostly conceptual levels of algorithms that we use for robot navigation. So, before we proceed on to the section, I would like to have a brief overview of all the topics that we have covered so far. So, in week one, we have actually covered a basic introduction to various robotic systems, right? Like we have actually seen, what are the robotic systems that we have? We have robotic manipulators, then we have mobile robots, and then we have seen further classifications in mobile robots, which comprises of, mobile robots that work that can operate in air, in underwater, in land. And then we further narrowed our options in land-based mobile robots into legged robots, wheel mobile robots, tracked robots. And then further, finally, we actually focused the topic of our course onto mobile robots. Then we have seen the concepts of degrees of freedom. We have seen the definitions of degree of maneuverability and then degree of mobility, all those various degrees that are relevant to our course. Then for week two, we have actually covered the kinematic modeling of various configurations of wheel mobile robots, right? We have actually seen what are holonomic and non-holonomic mobile robots, what are their capabilities, how would you identify whether a mobile robot is holonomic or not? And then we have seen various different configurations, right? We have configurations of wheel mobile robots, those with those which are very similar to a tricycle, then those similar to an automobile, right, with two driven and steerable wheels at the front and two passive wheels at the back. Then we have seen configurations that uses unconventional wheels, right, such as the ones with the four mechanism wheels and the one with three omni wheels. So, like we have discussed the kinematics of all different configurations of wheel mobile robots in week two, and then in week three, we have actually derived the dynamic model of wheel mobile robots. So these are basically the governing equations. They determine the state at each instant of time. Depending on what all forces that are interacting on the mobile robot. We have actually discussed on how to derive these governing equations of motion using two different schemes. The first one being Euler-Lagrange methods, and the second being the Newton-Euler method. More or less, either of these two methods more or less give you the same outputs, which is in fact the governing equations of motion. And week four, we had a slight shift in our topics, week 4 to 6, right? So in week four, we discussed about how a mobile robot would perceive its environment, using sensors, the different sensors that a mobile robot would use to perceive its environment. And week five, we have discussed topics on localization and map building, right? So, like once a robot has, grasped some idea about the environment, it has to localize itself within that map or within its environment. So, like we have seen several methods, a couple of methods where to facilitate this localization, right? The first one we discussed was this Markov localization, and the second one that we have seen was using the Kalman filter localization. And then now we have actually reached week six, where we would be discussing navigation, right? So, like, let us revisit the flow chart of a wheel mobile robot. And let's see where we are currently for this week. So we have actually seen this flow chart at the beginning of week 4 as well as on week 5. So the process of the entire subsystems of perception, localization, and navigation can be represented by this image, where we'll consider this as a beginning point, the starting point. So the robot would use the sensors available to it to have an understanding of the environment that it is deployed on, right? To perceive or to extract useful information from the environment using sensors. And we have discussed these topics on week 4, regarding perception. And for week 5, we have covered the localization, where from the information that we gathered from by perception, from the sensors, and from whatever information that we can gather from the encoder readings, we fuse these informations, one from the internal encoders of the robot and one from the sensors, which would facilitate localizing the robot within the map that it created. So once it has understood its position within the map, like for example, if the map, what I'm saying, either it could be fed into the robot, right? We can actually the robot can actually download a map from the user, and once it has, or it could simultaneously create a map as it moves around its environment. So either ways, you can assume that by localization, it already has a map with it, and it also as it already done its localization, it knows its start position, and it also knows its goal position, right? And within this map, it will be there will be a lot of obstacles, or a lot of things or objects that it has to avoid while it is navigating through that environment. So where we are on week 6 is somewhere around here. The contents of our topic will be somewhere around here. So like once it has created a map, it has to find it has to actually find an optimal path, so that it can reach from its start position all the way to its goal position, and at the same time, it should not collide, or it should not make any sort of interference with these sort of obstacles, right? As you can see, there are plenty of paths that you can use to reach the goal position, from the start position. And navigation essentially deals with finding an optimal path using several of the algorithms that we would be discussing in this session. So the definition given in the course for navigation is, given a partial knowledge about its environment and a goal position or series of positions. It could be a goal position, or it could be a series of position, starting from the start position all the way to the goal position. Navigation encompasses the ability of the robot to act based on its knowledge and sensor values, so as to reach its goal position as efficiently, as reliably as possible. So as it moves within its map or within its environment, it keeps on getting feedback from its sensors, and it also has to use that information so that it can reliably, without encountering any of these obstacles in a in a destructive way. It has to reach the goal position in a reliable way, and also it also has to reach in an efficient way, without spending too much energy in order to reach that goal position. So let's see some of the key features, important capabilities of navigation. So what exactly do we expect from the navigation part? So the first thing what we expect the navigation system to do is path planning, right? Which is nothing but identifying a trajectory that will cause the robot to reach the goal location when executed. So like there could be plenty of such trajectories, right? Maybe I'll just copy paste this map. So like as I was saying, there could be plenty of such, yeah, if I consider, paste it over here, there could be multiple such paths, right? From the start position, there could be multiple such paths which that can navigate through, that can basically navigate through the obstacles. So the trajectory will have the navigation subsystem should be able to identify a trajectory or trajectories that will cause the robot to reach the goal location when executed. And then obstacle avoidance. That is the second feature that we expect from the navigation system. So it says, given a real-time sensor readings, modulating the trajectory of the robot in order to avoid collisions, right? So in this example, I've considered the obstacles to be static. It does not really move in the environment. But there are a lot of practical situations where the position of the obstacles changes with respect to time. So initially, the robot may have found out an optimal trajectory, a trajectory that it spends very minimal effort. But as the robot executes this trajectory, and if suddenly an obstacle comes, into that trajectory, it has to modulate or it has to adapt around that obstacle so that it won't face any collisions with the obstacles. Right. One common example that I can give you is, the vacuum cleaner robots like this Rupa. Like when it is deployed in a room, it basically creates a map and it calculates where it has to go, within a room. But suddenly, if a person comes in front of it, you can consider the person to be a dynamic obstacle, right? So if a person suddenly comes into it, it has to move away from that person. It has to move away so that it won't collide with that person or an obstacle. So it has to dynamically adapt its trajectory in real time, as per the sensor readings. So that's about it. What we expect from the navigation subsystem. First is it has to identify the optimal path, and then while executing that optimal path, it has to actively adapt around that optimal path so that any collision with dynamically moving obstacles can be avoided. Then what are the other assumptions that we make? So assumption is that the robot is actually holonomic. That is one of the assumptions that we do for while we are developing navigation algorithms. So the total number of controllable degree of freedom is equal to the total number of degrees of freedom. So I hope you can recall from week two that the total number of degrees of freedom for a wheel mobile robot is actually 3, right? So if you consider this to be the chassis of a mobile robot, the entire rigid body of this robot can be fully defined by a frame of reference that is attached to the rigid body or to the chassis of the mobile robot. So if I call this as XB and YB, and if I denote a global frame of reference or an inertial frame of reference over here attached to the ground, XI and YI, you need 3 coordinates to fully define the position and orientation of this rigid body, right? You need 2 positions to define the origin of this frame, right? One coordinate along x-axis and one coordinate along y-axis, and you also need one coordinate to specify the orientation of this frame of reference with respect to this ground fixed frame of reference, right? You can use that by this degree of freedom called theta or psi, as what we use in our course. So the degree of freedom is always going to be 3 for a wheel mobile robot. But what about the controllable degrees of freedom? So this is where the concept of whether the system is holonomic or not holonomic comes into play. You have actually seen the degree of maneuverability is nothing but the degree of mobility and degree of steerability. And the degree of maneuverability should at least be equal to 3 for a robot to be holonomic. And we have actually seen several systems that are holonomic, right? The one that uses 4 Mecanum wheels is a holonomic robot, right? Because these holonomic robots can move in all 3 degrees of freedom, right? It can move forward, it can move backward, it can rotate about its own axis like that, with zero turning radius. It can move in the lateral direction, upward and downward. It can even move diagonal ways like this, right? So it's highly maneuverable, these holonomic robots. But in case of a non-holonomic robot, like a car, like a four-wheel car like structure, like if I depict this as a four-wheeler sort of a thing, you can consider the front wheels to be steerable like so, and the rear wheels to be just passive wheels. So I'll just depict these passive wheels using green color, and this driven and steerable wheels with this red color, right? So these robots, their motion capabilities are like they can go forward, they can go backward, but they cannot turn about its own axis with zero turning radius, right? Because a car, if you know how a car moves, I think everyone knows how a car moves. So these cars turn with a finite turning radius, right? It cannot turn about its own axis just like that, right? It can only turn in a finite turning radius like this or like this, right? And a car cannot slide laterally like this. It cannot slide laterally. It cannot move diagonally like this. No way that is possible. So, like if you want to parallel park a car in a slot like this, right? If you consider this to be one car and if you consider this to be another car, and if you want your car to park, in this slot, in this space, what you do, you first move your car into this position, then you reverse like this, and then you try to align it like that, right? So it takes multiple steps for a non-holonomic robot to achieve some specific position within the space. But holonomic robot, it can simply slide laterally just like that. One simple swift motion can achieve the same result. But a car, it has to go forward like this. It has to come backward. Then it has to, come all the way. Then it has to straighten so that it can be aligned with it. Yeah. So that's about holonomic and non-holonomic robots. And we assume that our robots are actually holonomic. That was the first assumption. And the second assumption is we consider our robot to be a simple point, right? So, for example, if we have a robot of a physical size like this, and if we have an obstacle like this, right? So, we consider a collision would happen. We consider a collision occurs when this robot comes into touch with this obstacle. Like so, if it is like this, we consider a collision to occur. So in our modeling, what we do is that we consider the robot to be a point, and the obstacle we accommodate or we compensate for that point robot by inflating the size of this obstacle, right? So whatever change that we got into due to the due to considering this robot into a point, we try to compensate by inflating the size of the obstacle. So like if you consider this to be the inflated size of the obstacle, to account for that shrinking of the robot into a point, right? So we consider the collision to occur when this point actually crosses this inflated area or this inflated perimeter. So like both are equivalent, but if you are considering the robot to be a point, it makes your calculations much more easier, right? It basically you can basically consider the collision to occur right as when this point crosses this line. But here in this case, it will be a bit ambiguous, right? You don't know which point crosses first. So this makes our modeling much more easier. And since our robot is holonomic, the most probably that orientation is not going to matter because holonomic robot can move in any orientation. So those were the two assumptions that we made in path planning, or while we are while we are discussing path planning algorithms. Then moving on, what are the methods, or what are the stages of path planning? So before we discuss anything regarding that, we first need to identify what are the inputs to a path planning algorithms, right? So if I consider a flow chart like this, path planning. So the inputs to the path planning would be a map, right? A map that is produced during that localization and map building phase, whatever we discussed in week 4. And since we have done the localization, we also know the position of the robot. I call this start. And I also know this the end position or the goal position. I also know how the obstacles are distributed. This can change, right? This can change in real time, as the robot moves. So once we feed this into the path planning algorithm, what we expect from the path planning algorithm is that the output from the path planning is that it will create, or it will so like for the time being, I'll just reproduce this, or I'll just copy this map, place it over here. Yeah. So from the output of the path planning algorithm, we expect the path planning algorithm to return multiple trajectories, right? From the start position to the end position. This is what we expect from the path planning algorithm, right? Multiple paths. And you may call this as road maps, a network of multiple trajectories, within that map. And then while it has to create this sort of roadmaps, all possible roadmaps, and then it should also select the most efficient or most appropriate, and as well as the most reliable path, so that it can reliably and efficiently reach the end position from the start position. So this would be the input to the path planning algorithm, and this would be the output of the path planning algorithm. So we can essentially split this process into two, right? First, being the creation of these trajectories, these creations of these roadmaps. So we call that first phase as graph construction, right? Constructing all these trajectories, and then computing that optimal path from all of these graphs. We call it as graph search, right? Finding out the optimal trajectory. That we call it as graph search. Right, so we'll discuss the algorithms for both, or methodologies for constructing the graph, or the graph construction, and graph search. So these two together constitute the entire path planning algorithms. Right. So we'll go by these points briefly. In graph search theory, a connectivity graph in free space is first connected and then searched. So as I was telling, we create a connectivity graph first, and then it is searched. The constructing phase is what we call graph construction, and the searching space is what we call the graph search. The graph construction phase is often performed offline. It does not have to be in real time. You can do that with the map that has already been created. So the two main steps are graph construction, where the nodes are placed and are connected via the edges. Graph searches, where the computation of an optimal solution is performed. So the following are the various graph construction methods. So we'll be covering these three different types of algorithms for graph construction. The first one is visibility graph. where the path comes as close as possible to the obstacles and resulting in a paths that are minimum length solutions. Right, so these paths forces the robot to be as close as possible to the obstacles, and that makes that makes the paths inherently minimal length solutions, right? So if I consider this to be the start position and this to be the position, this is you can consider this to be the minimal length solutions, right? And these are the length of any other paths are basically of higher lengths or of higher distances. And the second method is what we call this a Voronoi diagram. So the philosophy is entirely opposite to the visibility graph. It says the path stays as far as possible from the obstacles. Right? Earlier it was as close as possible to the obstacles. Now it is as far as possible from the obstacles. And the third is the cell decomposition methods. Right. So the idea is to discriminate between free space and occupied space. Like we'll discuss more on that in the upcoming slides, in detail. So these are the specifics for the first method. First method on graph construction, what we call as the visibility graph. So you can consider the image. You can consider this image to be the map that you have been given, right? So you have a map of the environment, right? You have a start position, and uh, you have a goal position like this, like so, and you could consider these as the obstacles, right? So let's see the visibility graph for a polygonal configuration space consisting of edges joining all pairs of vertices that can see each other, including both internal initial and goal positions as vertices as well. So over here, what you see is actually a polygonal configuration space. Like all the obstacles are mapped as a polygon. And as you can see, each of these nodes you could call them as vertices. This is one vertex. This is one vertex. This is one vertex. These are all vertices within this polygonal configuration space. So this is the first step. You first identify all the vertices within the configuration space, including the start and the goal position, right? And the next step is actually to connect two vertices that can actually see each other. So what do you mean by connecting the graphs or connecting the nodes that can see each other? So if this is a node and if this is a node, these two nodes are in the direct line of sight within among each of them, each other, right? So these two nodes can see each other. Like if you are a person standing here, you can actually see the person standing here without any obstruction. And same goes for this node and this node. They are directly in a line of sight. But what about this node and this node? Right? They are not directly in line of sight, right? Because there is an obstacle in between. So if a person is standing here and if a person is standing there, they cannot see each other, right? Because of this obstacle. And same goes for this node and this node. They are not in line of sight because there are two obstacles. That is obstructing the field of view. So the second method is like once you have identified the nodes of the configuration space, we connect the nodes that can basically see each other. So this this could be one connection. Uh, yeah, this is another connection. This is another connection. The nodes that can see each other. You can connect like so. You can connect like so, like so. So all connections where two nodes can see each other, you connect those two nodes, all possible combinations, right? And at the end, you will end up with uh, a network or a roadmap like a roadmap like that has been depicted in this figure. A multiple crisscross. We call them as roadmaps. And once a roadmap has been created, the next phase would be to search for a path that actually takes the minimal distance from the start node to the goal node. Right. So as you can see, this node this path that is highlighted in this thick black color is actually the minimal distance. That it takes the least amount of distance to reach from the start position to the goal position, right? So any other path or any other road, like if I go like this, like this, like this, like this, it takes more distance. Or any other combination like this, it can, all these are possible combinations. So all of these combinations would take more distance as compared to this path. And as you can see, the optimal path goes as close as possible to the obstacles. This is how the philosophy of the visibility graph basically work, right? This is an obstacle. So at this position, the robot is very close to this obstacle, and same goes for this obstacle as well, right? So at this position, the robot is, it's extremely close to this obstacle, right? So the advantage is that, this method of graph construction, it would give you a very minimal distance path from the start position to the goal position. But a disadvantage that you could think about is that this algorithm makes the obstacle to go as close as possible to the obstacles. Actually, makes the robot to go as close as possible to the robots. So you could consider that to be a disadvantage because it creates some sort of a safety concern. So that is about visibility graph. And now we move on to Voronoi diagram. So this basically has entirely opposite philosophy when compared with the visibility graph. Here, the algorithm forces the robot to be as far as possible from all the obstacle, right? So if you consider this to be the start position and this to be the goal position, uh, so if the robot is at this location, right, there are two obstacles that are very near at this position. So if I highlight this position, the two obstacles that are very near are, this corner or this edge of this obstacle, and this, if you consider this to be the boundary wall of the map, these two are the obstacles uh, that are close to the robot when the robot is at this location. So Voronoi method basically forces the robot to be as far as possible from all the obstacles, right? So it basically forces the robot to be at the middle, or right at the middle between the two obstacle spaces, like so. So this point is somewhat in the middle, between these two obstacles. And as the robot or as the robot goes anywhere in the map, the algorithm essentially uh, tries to position itself so that it is as far as possible from all the obstacles. Right. One more example, if you want to see, if the robot is at this position, right, the two obstacles that is in the near vicinity would be this edge as well as this edge. So the only position that maximizes the distance between these two obstacles is exactly this, this position. It cannot be here, it cannot be here, it cannot be any closer to this obstacle. So with that principle, it basically creates, a map that looks something like a ridge, right? A ridge is where a ridge is something like a valley, and in this context, it is actually equidistant from all the nearby obstacles. So let's see the definition. For each point in the free space, its distance to the nearest obstacle is computed, using its available proximity sensors. At the points that are equidistant from two or more obstacles, such a distance plot has sharp ridges. So whatever you see in this diagram, these are called the ridges. The Voronoi diagram consists of the edges formed by these sharp ridges. So throughout this map, it actually creates a ridge, where each of these of these ridges are as far as possible from the nearest obstacle, right? So since the path planning algorithm makes the distance between the robot and the objects in the environment, right, it tries to maximize the distance between the robot and the obstacles. Any short range sensor on the robot will be in danger of failing to sense its surroundings. So what it means is that, like, if there are two obstacles, if you consider this to be one wall, and if you consider, this to be the second wall, and if this is a robot, right? So Voronoi method essentially tries to maximize the distance between the obstacles, right? It the Voronoi diagram. If the robot is here, the Voronoi diagram tries to make it at the middle, right here, right? Or if the robot is here, it'll push the robot away from this edge, so that it'll be as far as possible from both of these obstacles, right? But there could be an issue if the distance is actually very large, right? And if it is using some short range sensor, the sensor won't be able to detect the boundaries anymore, right? It won't be able to detect the boundaries anymore because this distance is actually very large, and the sensor is actually short range, so it won't be able to detect the environment any further. So, that could be a potential drawback of this Voronoi concept, where it tries to force the robot to be as far as possible from the obstacles. And eventually, there could be a situation where it cannot no longer detect that obstacle because the sensor range falls short of that. Right. So using that principle, once it has created a map, then it will basically find, you can use some graph search method to find the optimal path. As you can see, from all the ridges available, the optimal path seems to be this one, like so, right? Because that takes the least distance. Like any other path like this, or, like this, they take more distance than the optimal path that is depicted over here. So we have seen two methods for graph construction. We'll see the third method. We call this as the exact cell decomposition method. So once again, we have an obstacle space, where you have this obstacles, uh, and the map. You also have a start position and a goal position. So let's see how the algorithm works for this exact cell decomposition. So here, the boundary of the cells is based on geometric criticality. How it basically, how you discretize or how you, split your map depends on the nature of the geometry of these obstacles or the objects within the map. The resulting cells are either completely free or completely occupied, right? So depending on the vertices that you have, based on the geometric criticality, you can divide the map like so. You can simply create some vertical lines through each of these vertices, right? And you can see whether once you do this, you are essentially creating a lot of cells like so, right? and these are all these can be sequentially numbered. And the motion of the robot is entirely dependent on the fact that whether the cells are free or whether the cells are completely free or completely occupied. The second point is the basic abstraction behind such a decomposition is that the particular position of the robot within each cell of the free space does not matter. So the philosophy is that the location of the robot within each of the cells is not a matter of concern, right? There could be a lot of application where the robot. It's fine to have a robot position anywhere within the space. Maybe you can force a robot to be within the midpoint of the cell. So the only thing is, it has to be within the cell. Any other thing should not really matter. Right? What matters is rather the robot's ability to traverse from each free cell to the adjacent free cell. So as long as the robot can successfully navigate from one free cell to the adjacent free cell, this is all what we actually want. Right? It can move in many number of ways. It can move. It can go like this. It can go like this. It can go like this. It can go, like this. Many number of possible options are possible, right? So then what is next? The key disadvantage of exact cell decomposition is that the number of cells and the overall computational planning efficiency depends on the density and the complexity of the environment, right? So how are we basically creating these cells depends on the obstacles that we have in the environment, right? So if we have a very sparse environment like this, and if you have a map, if you have a start position, and if you have a goal position, and if you only have a single obstacle like this, you will have a very sparse discretization like this, right? Maybe you have one, you have two, you have three, you have four cells. So again, this is actually very sparse. So it does not, it may not give you the right amount of uh, accuracy or right amount of resolution that you wish, right? But if there are more obstacles or there are more features within this environment, the level of resolution or the level of discretization would increase. So as you can see, the point basically says, the efficiency and the computational planning is actually a function of the density, the number of obstacles as well as the complexity of the obstacles, in the environment. Complexity means, how you could easily correlate with, how many vertices these obstacles may have. If it is a single obstacle with two vertices, it will basically divide the space into two cells. But if it has three vertices, we basically divided it into four cells, like so. So, the number of vertices you can directly correlate with the complexity of the objects, and the number of such obstacles, that you can correlate that with the density, the number of obstacles within the space. Right. So that's how basically the cell decomposition works. So and then once it has a start position, it will determine which of the cells are adjacent to each other, right? And then it tries to create a connectivity map, right? So if it starts from cell 7, the cells adjacent to cell 7 is cell 1 and cell 8. Then adjacent to cell 8, you have cell 9, and adjacent to frame 1, you have cell 2. So based on this adjacency connectivity, it tries to create several, connectivity. It tries to create several route maps like this. Right? This is one possible option. This is another possible option. This is, this is one option. It can go like this, another option. But it cannot jump from one cell to another cell, right? All the cells have to be connected. All right. Then once it has created several such roadmaps, it will basically select the most ideal or most the path which has minimal distance using some graph search methods. Graph search methods. All right. So now we have seen three graph construction methods. The first one was visibility diagrams, visibility graphs. Then we have seen Voronoi diagrams, and finally we have seen this exact cell decomposition. I believe we have one more variant actually. It's called approximate cell decomposition method. So what we do is we discretize the grid based on our requirement. We can give a predefined level of discretization, and then we can discretize the entire map based on the level that we specify. So just like before, we have several obstacles. We have a start position, and then we have a goal position, and basically we discretize the grid based on the required level, our required level of resolution, and based on whether or not these obstacles are filled. Sorry, these grids are filled by this obstacle. We basically have this sort of tessellation, right? So if one of the cells is filled by the obstacle, we consider that cell to be completely filled, right? Or if there is some fraction of an obstacle within one cell, we block that cell. We basically block that cell. So once we do that, once we map the obstacles into this fine grid, you will end up with a discretization like so. A very highly pixelated obstacles rather than this highly definite obstacles, right? So then what are the features, what are the drawbacks, and what are the pros and what are the cons? So these are actually very popular, right? This method is actually very popular because it's far more easier for us to implement, right? It's easy to create a grid of a map, and then it's easy to block each of these blocks, or we can actually block or we can restrict each of these individual grid point based on whether or not there is a part of the obstacle within this grid point. So the world is tessellated, like so, transforming the continuous real environments into discrete approximation for the map, which depicts what happens to the obstacle filled and free areas during the transformation. So if this space is free from obstacle, that is kept as free. If any fraction of the grid is actually occupied by an obstacle, we remove that point, or we make that point inaccessible for the robot. And there are drawbacks, since we are using this sort of tessellation. It's possible for narrow passageways to be lost during such a transformation, right? As you can see in this representation, when we have not transformed our obstacles, it's fairly obvious to see that the most efficient path from the start position to the goal position would be something like this, right? That is the path that takes the minimal distance. But once you perform the tessellation, or once you transform your continuous obstacles into this discrete space, this path would look something like this. And as you can see here, it is basically considered to be blocked by by these two transformation, or those two representation of the obstacles. So there is a possibility that these narrow passageways could be lost due to these sort of transformations. So instead of the robot going like this, now the robot considers this area to be blocked. This area to be kind of consisting of obstacles. So it will try to find another path. It will try to find a path like this, or it will try to find a path like this. Right, but whatever path it determines, it is always going to be suboptimal, because we always know that this path exists in real life, right? It always exists in real life, but the robot thinks that it's actually blocked off. So it tries to go like this, or it tries to go like this. So whatever path it chooses is always going to be suboptimal. right? Because these sort of narrow passageways can get lost during such transformations. All right, now we have actually seen graph construction methods. Now we move on to graph search methods, right? Once we have created these sort of roadmaps, how do we select the optimal? How do we select this optimal path out of all the possible paths? So that is the topic what we discuss in graph search. So let us look at some of the salient features of the graph search approaches. So the first point says earlier in graph construction, the environment map has been converted into a connectivity graph, right? So if you want to recall, whatever you have over here, these ridges in Voronoi diagram or this network, within that visibility graph, these are all called as uh, the connectivity graph. Multiple sort of connectivity graphs are available. Okay, that was about the first graph. We already have made a connectivity graph. Second point, whatever map representation is chosen, the goal of the path planning is to find the best path in the map's connectivity graph between the start and goal. Right. So whatever map representation is chosen, be it visibility graph, be it Voronoi, be it exact cell decomposition, be it approximate cell decomposition. The purpose of the graph search is to find the optimal path from all the other roadmaps or all the other connectivity graphs. So here, the keyword best refers to the preferred optimization criteria, right? It does not have to be a single criteria. It could be the shortest path, it could be the shortest time, it could be shortest travel cost, etc. Now, one might think that, this could mean the same thing, right? So one example I can tell you is that if you have a start position here, and if you have a goal position here, and if you consider, a straight line connecting the start and the goal position to be uh, a path that has minimal distance, you could argue that, this path represents, the path with shortest path, it could be the shortest path. And you could also argue that since this path is the shortest path, you could also, this path is also the shortest time path, right? If a path takes the least amount of time, that should also take the shortest amount of time, right? Than any other path like this, any other convoluted path. Right? One could argue that both are the same. Or you could also say the shortest travel cost. Travel cost could be in terms of energy, right? You could spend the least amount of energy if you are going in a straight line, than going in a twisted curve sort of a way. But that is necessarily not always the case. The reason is that if you consider a case where, if I say that, these the straight line path is actually very rough, it's very mountainous, or if there is a big mountain uh, or a big hill somewhere in between the path, and the robot will have to spend considerable amount of energy to climb that hill, right? Or it's very rough, so it creates a lot of additional energy requirements to navigate through that to this through this rough path. So many a times, in a lot of practical situations, taking a curved path, which could be relatively much smoother, could be much more cheaper, right? You could get, if this path is smoother, much more smoother, you could reach the goal position with this curved path with shortest time and shortest traveling cost, right? Or you could take any other path. Even though the length is more, right? You could effectively reach the goal position in a shorter time or in a lesser time, and while spending lesser traveling cost. If that path is actually very smooth, right? So that could be one of the practical cases where taking a longer path could be much more feasible or could be much more efficient, right? And the optimization criteria what we use is defined by this expression where this f of n is nothing but the expected total cost, right? The cost that you require from moving from the start position to the goal position. This is expressed as a sum of g of n, which we call as the path cost, and another variable called h of n, which is what we call as the heuristic cost, right? Path cost, maybe you can consider the path cost. Path cost has to be something. The energy that you need to you have to spend so that the robot can move from one position to another position, right? So if you are moving one unit to the left, one unit to the right, you can consider the path cost to be 1 unit. Or if it is moving upward by 1 unit, it is still moving the same distance. So you can consider this g of n to be 1 unit. But the heuristic cost could be something else, right? So if I say that this path is rough, right? I could assign a higher heuristic cost to this path, right? Maybe if this path is rough path, maybe I can assign this h of n to be probably 0.7. But if this path is smooth, I could maybe assign the heuristic cost h of n to be very low, zero point 0.1, right? So even though the path cost, even though the energy that you spend to move from this position to this position or this position to this position is the same, right? 1 unit and 1 unit, the heuristic cost is actually different. So if you take a sum of this path cost and heuristic cost to move in this vertical smooth direction, you only require 1.1 units of energy, which is your f of n. And if you want to move in this horizontal direction, you have to spend uh, 1 plus 0.7, that is 1.7. This would be your expected total cost. So the robot would naturally take the path with lower expected cost, which would be, this direction. If it has a choice to move in this direction and this direction, it will obviously take a decision to move in the direction which has the least amount of expected cost, right? So we'll see some of the algorithms. So there are two algorithms which can be used to find the optimal or to find the total distances between the start and end position. The first one is what we call the breadth first algorithm, right? So the salient features are begins at the start node and explores all its neighboring nodes. Then for each of these nodes, its neighbors, it explores all their unexplored neighbors and so on, right? So all this connectivity graph, you can consider another representation of that connectivity graph. So if I call this as the start node, and there are many intermediate nodes in between. So I'll call this node 2, node 3, node 4, node 5, node 6, node 7, node 8, node 9, node 10, node 11, and at the end we have this goal position, right? And this, if I draw a connectivity diagram, this connectivity you can easily obtain it from that. You will obtain it from the graph search method, right? So sorry, the graph construction method. You will obtain this sort of connectivity through the graph search method. And finally, you have this goal position. So this 11 is connected to the goal position, 8 is connected to the goal position, and 10 is connected to the goal position. So what the breadth first algorithm does is it begins at the start node, right? So it begins at the start node and then it explores all its neighboring nodes. So what are the neighboring nodes? The neighboring nodes are actually connected directly to the start node. So this node 2 is connected to the start node. Node 5 is connected to the start node. 4 so this is 3 actually. Nodes 2, 3, 4, and 5 are connected to the start node. So like we'll first, compute the cost for reaching to this neighboring node. So I'll label this. First we explore node 2, node 5, node 3, node 4, and node 5. And then we'll see then we'll move into this level, right? This has already been explored. Then we'll explore this level of nodes. So now node 2, the only neighbor that node 2 is connected is node 6. So then we'll explore node 6, right? Then node 5 is actually the neighborhood of node 5 is node 6, node 7, and node 4, right? So node 4 is already explored. Node 6 is already explored. So we'll explore node 7. And node 4, neighborhood points of node 4 are node 5, node 8. I think that's about it. So node 8 is what we'll explore in the next phase. Node 8. So like I'll just write it serially, all the nodes that we have explored. First, we have explored the start node. First we have explored the start node. Then we have explored node 2, node 5, node 3, node 4, node 5. And from node 2, we have explored node 6. Then we have explored node 7. Then we have explored node 8. And the remaining node that is yet to be explored in this level was node 5. So 8 is explored. Then 9 is not explored because 9 is in neighborhood of node 5. So then we'll explore node 5. Node 9. So I'll label it over here. Node 9 has been explored. Now we move on to this level, right? So we'll start from node 6. So neighborhood of node 6 is node 10. So node 10 will be explored. Then neighborhood of node 7, all the neighborhood points have been explored. And what about node 8? So in node 8, the neighborhood points are node 11 and the goal position. So we'll explore node 11. We'll explore node 11 and the goal position. So 11 and goal position. So this is how it basically evaluates. One second. This is how basically the breadth first algorithm evaluates the cost needed for exploring all the nodes. Right? It grows like a wildfire. Right? First it grows or explores in this level, then it explores in the another level, then it explores in another level. So it's like a spreading wildfire, right? That is about depth first, and this is how this is basically the order that we received for exploring the connectivity graph. Then what about depth first? So in depth first, it expands each node to its deepest level of the graph until the node has no more successors, right? Then the search backtracks by expanding the next neighboring node of the start node until its deepest node, and so on. It may visit previously visited nodes due to this as a part of its backtracking. So like by using the same example, Yeah, let's use the same example. So we have the start node, then we had node 2, node 3, node 4, node 5, then we had node 6, node 7, node 8, node 9, then we had node 10, then we had node 11, then we had the goal position. And let me reproduce whatever I have created in the earlier example. So start node is connected to 2, 5, 4, so 2, 3, 4, and 5. Then 2 is connected to 6, 3 is connected to 6 and 7. 4 is connected to 8. 3 is also connected to 4. Then 5 is connected to 8. 5 is connected to 9. 8 is connected to 9. 9 is connected to 11. 8 is connected to goal position. 8 is connected to 11. 11 is also connected to the goal position. 6 to 10, 7 is not connected. This is 10, 10 to goal position. And 8 to 10 also we have. I think this is pretty much it. So let us execute this depth first algorithm. So as it says, it expands each node to its deepest level. So if you are starting from start node, it will expand everything up to the deepest level until no there are no successors. So like if it goes like this, it straight away reaches its goal position. If it goes through this path, right? So one possible option is start 2, 6, 10, and then goal position. Right. So as you can see, it has actually reached all the way to the goal position in a much shorter way because it tries to expand, tries to expand all the nodes like this. It goes to the deepest level. So like suppose just to demonstrate the second point, I'll just assume that, there is no connection between 10 and the goal position, right? There is no connection like this. So what it will do? So it will first explore all the nodes until there is no more further successors. So it will explore node 2, node 6, and node 10, and it cannot go any level deeper from node level because node level is not further connected down. So what it does is it backtracks. It moves from 10 to 6, and then it tries to branches. It tries to branches uh, from 6 to some other point, right? So then it backtracks to node 10. Uh, yeah, actually it backtracks from node 10, and immediately it can actually go back to node 8, right? Then it tries to go deep from node 8. So it tries to go deep from node 8 like this, and it then reaches that goal position, right? So if you assume that there is no connection from node 10 to goal position, the path could be start 2, 6, 10, 8, then goal position, right? So, and in doing so, it actually explored node 2, 6, 10 in the first phase. And then in the backtracking phase, it didn't necessarily have to backtrack all the way. It only had to it took a side step like this. But if you consider, this path also not existent, it'll have to go back like this, right? It'll have to go back like this. So it'll backtrack, it'll visit the previously visited node, and then it try to take a diversion like this and try to explore in a depth-wise manner. So that's about breadth first and depth first. The difference in philosophy. And we'll use once we'll demonstrate one such method. The first one we call is at first one we call it as a grass-fire algorithm. So this is that a map of the environment. You consider this to be the start position, and you consider this to be the goal position, and you assign the path cost g of n to be 0 at the goal position, right? The total expected cost f of n is g of n plus h of n, which is the heuristic cost. So in grass-fire algorithm, we consider this heuristic cost to be 0, and we assign the path cost at the goal position to be 0. And every step you make, into this following blocks, you assign a path cost to be 1 unit. So 1 unit movement would cost you, 1 g of n would be 1. The path cost would be 1. Similarly, if you move in this direction, your path cost would be 1. Similarly, if you move from here to here, the path cost would be 1. And if you move from here to here, the path cost would be 1. Right? And what about these diagonal points? You will have to move 1 unit in this direction and 1 unit in this direction. So your path cost would be 1 plus 1, 2. Here also 2, 2, 2. Right? And what about this node? Right? You have to move 2 units in this direction, 1 unit to here and 1 unit to here. So the path cost of this node would be 2. And similarly, this node would be 3. And in using the same logic, this would be 3, this would be 3, this would be 4, this would be 5, 6. And if this is 5, moving 1 unit in this direction, it could be, this column could also be 6. And then you have 7, you have 8, you have 8, you have 9, you have 10. This is also 9. And since this is 3, this is 4, this is 5, this is also 5, this is 6, 7, 8, 9. Right? Now, you move along this successive numbers. This is one path. You can move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is one path, which would consume some amount of energy. Right? I'll just label it like that. So this is one feasible path. If you start from the goal position, if you backtrack it like so, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a feasible path. And this is also another feasible path. 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, 10. So that also spends the same amount of energy as compared to the blue path. There is one more path that is feasible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can also go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is also feasible. This all path is also feasible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is also one more path. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all these multiple paths, all these options are actually possible. They are considered to have, they are considered to spend same amount of energy or same amount of total expected cost. Right? But if you try to go like this, 1, 2, then from 2, it has to go to 1. So that is also not very optimal, right? Then it has to go to 2, 3. So the total cost will always be more than simply 1, 2, 3, 4. If you take a sum of 1, 2, 3, 4, 5, 6, 7, 8, 9, that path will have the least amount of cost. But if you try to go in some other way, 1, 2, 3, then again 2, 3, 4, 5, that will be obviously taking a lot of, it will result in more expected cost, than these previously highlighted optimal points. So as you can see, it's called a grass-fire algorithm. This is an example of the breadth-first algorithm, right? So we assign one at the proximity, then we have this two, then we assign three to the next neighboring point. So like it grows, radially outward like this, just like how a wildfire would propagate, from this origin, it will grow outward. So with this path, with these optimal paths, then we'll execute, one of these paths, from the start position to the goal position. Any of this path is considered to have uh, the same amount of total expected cost. So that is about Grass-Fire algorithm. Then there is something called Dijkstra algorithm. Actually, this is f of x is g of x plus, I think, f of n, right? F of n is nothing but g of n plus h of n. So in earlier case, the movement from one node to another node is considered to have equal uh, path cost, right? If it moves from one node to another node, you consider the path cost to be one. It increments by 1 units. But in Dijkstra, depending on the node that you are moving to, this g of n is actually varying. It varies. So, for example, if you are moving from path 1 to path 2, the path cost is 9. And if you are moving from path this node, start node, to the node 6, the path cost is 40. Right? But in the Grassfire algorithm, everything was the same. Everything was incremented by 1. Movement from one node to another node is incremented by 1. But here this is actually different. And in Dijkstra algorithm, we consider the heuristic cost to be 0. Right? So what are the salient features of this Dijkstra algorithm? So it says this is similar to the breadth first search, except that the edge cost may assume any positive value. So instead of g of n being constant, it can assume any values. So this algorithm start by expanding all nodes similar to the breadth first search, right? Except that the neighbors of the expanded nodes are placed in a heap and reordered according to their cost, right? So the difference is that first you assign, infinite cost to all the nodes, infinity, 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 infinity. And similar to the breadth first, you start from the start position, right? And you explore all the neighboring nodes. So this is a neighboring node, this is a neighboring node, this is a neighboring node, right? So the cost to reach node 2 is 9 units. So you replace this infinity by 9, right? And then cost to reach node 6 would be 14. So you replace this with 14. And the next neighboring node is node 7. And the cost to reach node 7 is actually 15, right? And if you go by the breadth first algorithm, you can basically explore any of these nodes. This could be becomes the part of the next level. So going by the breadth first, you could explore any of these nodes. But in Dijkstra, it says except that the neighbors of the expanded nodes are placed in a heap and reordered according to their cost. So we basically classify them according to their cost. So as you can see, node 2 has the lowest cost and node 7 has the highest cost. So since node 2 has the highest cost, we explore node 2 first, within this heap, right? So if you explore node 9, the next neighboring node is node 3, and the cost would be 24. So I'll replace this infinity with 24. Now, how many unexplored nodes you have? You have this node 24, you have this node 14, you have this node 15, and all the others are infinity. And then again, you place all of these nodes in a heap, right? And then you select the node which has the least cost, which is node 6, that has the cost of 14. And then you explore all the neighboring nodes of 14, which are, node 3, node 5, node 7, node S, right? And this keeps on, updating and updating and updating until you reach the goal position. So subsequently, the cheapest state on the heap is extracted and expanded. So we, just as we were talking, we extract the cheapest node and then we expand it. This continues until the goal node is expanded. Solution can then be backtracked from goal to start. Due to reordering in the heap, time complexity may increase. So like each time we are reordering, we have to backtrack, we have to expand it further. So that could be detrimental when the connectivity is actually far too complex. So like we'll see an example of this Dijkstra algorithm further down this lecture, then it will become more clear, I hope. Then next thing is what we call an A-star algorithm. Here, I'll just reproduce that expected total cost. F of n is the sum of g of n, the path cost, and the heuristic cost. So here, the heuristic cost is the sum of path cost and heuristic cost. So this is not zero anymore, right? The heuristic cost is taken as the distance of any cell from the goal in the absence of obstacle cell. So if I have a grid like this, right, and if I consider this to be the goal, and if I consider this to be the start position, and if this is my current position, so the heuristic cost is nothing but the distance from any cell, distance of any cell from the goal position in the absence of obstacle. So if this is goal position and if this is the current cell, it need 2 units, right? The distance between the goal cell and the current cell is 2 units here. 2 units. So the heuristic cost of this cell, h of n, is going to be 2. Right? What about this cell? So this is, since this is 1 unit from the goal position, the heuristic cost for that cell is 1. So on and so forth. So then the heap is ordered according to the smallest cost value that includes the heuristic function. Then you calculate the total cost. You take a sum of g of n and h of n, and you expand the nodes which has the least f of n. Keep on expanding and expanding. The lowest cost is then extracted and expanded. This continues until the goal node is expanded. The lowest cost solution can then be backtracked from the goal. It's very similar to the A-star algorithm. And here you can see how this thing propagates. Right? So initially we have a start position, right? And you know how to calculate this g of n, right? So the distance from the start position to this node is only 1 unit. So we have g of n to be of 1 unit. And same goes for this path. The distance from start to this node is only a single unit. And as a result, g of n is 1 unit. But what about this node? If you consider the Pythagoras theorem, this node diagonal is actually 1.4 or root 2 distance from the start node, right? Like so, right? Because it has to go 1 unit like this and 1 unit like this. So this distance is root 2, this distance. So that's why we have g of n as 1.4, and same goes for this node. This has 1.4 and this node has 1 units from this location. And what about this heuristic cost? Heuristic cost is nothing but the distance from this node from the goal position. So if you consider this to be the goal position, this cell is actually 2 units from the goal position. So that's why we have this heuristic cost to be 2 units. And this cell is actually 3 units from the goal position. So that's why we have 3 units over here. And what about this cell? This L is actually how many units? So if I try to move diagonally like this, you know, from here to here, this is 1.4, and from here to here, this is another 1.4. So total would be 2.8. So that's why we have 2.8 heuristic cost here. And what about this node? So from here to here, this is 1.4. From here to here, again 1.4. And from here to here, it is actually 1 unit. So 2.8 plus 1, we get 3.8 as the heuristic distance. So what we do is we add up the heuristic cost and the path cost. So I'll write that value in the middle. So 2 plus 1.4 is 3.4. Then 3 plus 1 is 4. Then 3.8 plus 1 is 4.8. Right? And 2.8 plus 1.4 is 4.2. Right? Then once we have estimated all the total expected cost, we just like what we did in the Dijkstra, we keep them in a heap, we arrange them in a heap, and then we try to expand the node which has the lowest total cost. So as you can see, in all these 4 nodes, the node that has the least cost is this one, right? Because it only has 3.4. Then we try to expand all the neighboring nodes of 3.4. But as you can see, all the neighboring nodes are, either already explored or are obstacles, not inaccessible, right? So this is actually blocked off. This is the start position that is also blocked off. Then we'll go with the next highest, next lowest total cost. So that will be this node 4, right? So that is also all the neighboring points of node 4 has also been explored, right? This is the start. This is 3.4. We have already explored that. So these are all blocked off. Then what is the next possible? Then the next is this 4.2, right? The next possible path that seems to be of interest would be yeah, I believe is this 4.2, right? This one 4.2. 4.2, right? Then we explore all the neighboring points of 4.2, right? We explore this one, we explore this one, we explore this one, we explore this one, we explore this one. All these nodes we will explore. So the total cost of this would be 2.4 plus 2.4. This is 4.8. This is 3.4 plus 2.8. This will be 6.2. Then this is 3.8 plus 2.4. This is again 6.2. Then 4.2 plus 2.8. This is 7, I believe. Right? Now, once we have estimated all the total cost, I think in this case, this is 3.8 plus 1.0, that is 4.8. Right? Then which node should we explore? We'll try to explore the nodes that has the least cost. So it's either this or either this, right? Both of them have equal low cost. So we could explore this, but all the neighboring nodes of this one has already been explored, right? This is explored, this is explored, this is explored, this is explored. So we'll go with this, right? So the neighboring nodes of this node is actually this, which are already explored. Then the remaining unexplored are this one, and this one. So that's how we get all these three things. Then we compute the total expected cost, and then we further carry out all the procedures. And then finally, we end up with an optimal solution. The thing is, we only have to connect all the parts, or all the parts which has the lowest expected cost. So once you do this, once you compute the total expected cost for all these explored points, it turns out that the path that I'm currently highlighting, this path has the lowermost or the lowest total expected cost at every point, right? So as you can see, this is 1.4, this is 2.8. So this is 4.2, this is also 4.2. This is again 4.8, and finally you reach goal. Actually, this one 4.8, 4.8. This is 4.8. Sorry, I made a mistake. This is 4.8. So these four nodes have the lowest total expected cost. So your ideal trajectory should be connecting all these ones, and every other path will have a higher than 4.8. So that's how this A star algorithm works. Then another way of this approach, for finding the ideal path is something what we call as this potential field path planning, right? So we create an artificial potential field, right? So the basic features are, it treats the robot as a point under the influence of an artificial potential field. So we basically create an artificial potential field where the obstacles are found to be uh, creating some outward potential, like a repelling force, and the goal position is actually an attractive uh, uh, sort of an entity. It attracts this artificial potential field. So any obstacle that you suspend in this field, it will repel from the obstacles, and it will, due to the influence of all the fields, it will get attracted into the goal position. But you have to, define, you have to design this potential field. How much each obstacle should repel, and how much this goal position should attract. Silent features are they treat the robots as a point under the influence of artificial potential field. The robot moves following this field. The goal acts as attractive force. The obstacles acts as repulsive force, and superposition of all these forces are applied to the robot. Right. So at this location, you have all these sort of forces, repulsive forces, attractive forces. And if you superpose all these forces, you will get a net force in one direction, the resultant of all the forces. And that resultant would determine in which direction that robot should move next. Right. So that's about this potential field path planning. Just a brief overview. And then there are some algorithms for obstacle avoidance, that you can incorporate into this navigation program. So like these are all self-explanatory. You have something called bug one algorithm. You have something called bug two algorithm. Depending on what should a robot do once it encounters an obstacle. These are very self-explanatory. You can visit the lectures to have an overview of these algorithms. So as of now, we'll solve some sample problems. We'll solve some problems that is more likely you can expect it during the similar sort of questions you can expect during during your assignments, weekly quizzes. So the essence of all these questions, we have discussed the essence for all these questions in this session. So I don't think I should be spending more time on discussing uh, or justifying the answers because we have essentially done an extensive review of all the relevant topics. So these sort of questions should be the answers should be straight away obvious, because these are mostly descriptive questions just to reinforce whatever we have learned, in the course of this week. Okay, so the polynomial configuration space consists of edges joining all pairs of vertices that can see each other. The above statement is suitable for which path planning method? If you can recall the summary of all the graph construction method, we have seen visibility graph, we have seen Voronoi diagram, and we have seen the cell decomposition method, and we have seen a fourth path called approximated cell decomposition method. So this statement basically is applicable to one of these four graph construction method. And based on what we have discussed so far, this is pretty much it's pretty much obvious that this is basically the philosophy of this visibility graph method for graph construction. So I hope that is clear enough. So that is indeed the answer. Moving on to second question. Which of the following comes under graph search algorithm? So depth first is a graph search algorithm. Cell decomposition is actually a graph construction method. We have seen this so far. We have seen in this from the earlier question itself. Breadth first is also a graph search algorithm. And visibility graph, this is also a graph construction. And Voronoi is a graph construction as well. So the question asks you to find the graph search algorithms, and we actually have two correct answers, which is options A and options C, depth first and breadth first. Those are the two graph search algorithms that we have come across in this course. So that is indeed the correct answers, options A and option C. Moving on to the third cost, the heuristic cost for all nodes in Dijkstra's algorithm is equal to, right? So we have this total expected cost. I think this is f of n as g of n plus h of n. So this is the total expected cost. And this one is the path cost. And this one is the heuristic cost. We have actually seen three graph search algorithms, which were the Graphsphere algorithm, we have seen the Dijkstra's algorithm, and finally we have seen this A star algorithm. And in both of these cases, the heuristic cost is 0. But for A star, the heuristic cost is not equal to 0, as per the examples that we have seen in the course. So for Dijkstra's algorithm, the heuristic cost is actually 0. should be clear enough. Okay, so moving on to question 4. Choose the true statements. The first statement says the potential field methods treats the objects as a point under the influence of artificial potential field. So that is a true statement because that is what we have just discussed. The second statement is the goal acts as a repulsive force and the obstacles as an attractive force. That is actually false. It's in fact it's the opposite of what it has been stated over here. So that is a false statement. And option C says the goal acts as an attractive force and the obstacle acts as a repulsive force. That's true. And statement 4 is the superposition of all the forces uh, applied to the robot, which in most cases is assumed to be a point in configuration fields. That is also right. Of all the forces or force fields acting on the robot, you superpose all the forces to find the net resultant of all the forces. So that net resultant basically determines along which direction the robot should move next. So in this case, our correct options are options A, option C, and option D. We have 3 correct options. So I hope that is fairly clear enough. We have 3 correct options. Moving on to question 5. Choose the algorithm shown below. So this is one of the obstacle avoidance algorithm that we have seen in the course. So as you can see here, the robot actually starts from a start position. Then as per the arrows depicted in this diagram, it encircles the obstacle once, right? And then it again goes around and somewhere around here it breaks off to the next obstacle, and here also it basically does a loop, and once it reaches this point it breaks away to the goal position. So this is the philosophy of this bug one algorithm, right? Where this bug one algorithm, the robot actually encircles the obstacle first, and then on the second pass it breaks away from the obstacle uh, in such a way that the distance to the next obstacle is actually minimum, right? So instead of breaking from here, here to here the distance is much higher, here to here any other distance is actually much higher, but at this point the distance from this point to this point is actually the least, right? And the same thing goes on in the next around the next obstacle, right? It goes in this direction, it encircles the object once, and at the point where the distance between the robot and the goal position is the minimum, it breaks off, right? So that is about this bug one algorithm. There is also a bug two algorithm, where it does not really make a loop around the obstacle. As long as it gets a line of sight to the next obstacle, it'll immediately break away to the next obstacle like this and like this, right? As long as it gets a sight of the next path or the next obstacle, it immediately breaks off. So the correct answer is indeed bug one algorithm, option B. Moving on to question 6. The below figure shows the start and the goal position for a robot to travel by avoiding obstacle polygons. The shortest path the robot can follow from the start position to the goal position using the visibility graph search method is. So there are multiple options given, which basically gives you the path through each of these nodes. So the first path is 15962. So 1, then it goes to 5, then it goes to 9, then it goes to 6, then it goes to 2. So this is obviously false, right? Because it cannot go from 1 to 5 because there is an obstacle in between. So that is obviously false. The second option is 162. So if this is 1, then where do we have node 6? Yeah, 1, 6 is like this, and then 2. Again, that is also not feasible, right? Because the path from 1 to 6 basically goes through this obstacle. So that is also not feasible. The third path is 1362. So 1, then you have 3, then you have 6, then you have 2. So I'll just redraw it more correctly or more clearly rather. So 1, 3, 6, 2. So that seems more like it, right? That seems to be the minimal distance of all the possible paths available. So this seems possible. Then another path is 1, 4, 12, 2. So 1, this is 4, this is 12, this is 2. So obviously this path has the minimal distance. It should be pretty apparent from the connectivity graphs that we have drawn. So here the correct path, the shortest path as per the visibility graph search method is indeed 1362, which is option C. Yes, that is indeed the correct answer. Then moving on to question 7, find the shortest path from S to T using Dijkstra's algorithm. So like we'll work out the Dijkstra's algorithm where it has varying path cost but zero heuristic cost. So as I was saying, we first assign very high uh, path cost to all the nodes at the beginning, right? So we will assign infinite path cost to all of these nodes, right? And then we try to expand the first node like so. So all the neighboring nodes of the first node is node 2, node 6, and node 7. So like we'll expand all the nodes from node 2, node 6, and node 7. So the cost for traveling from node 6 to node 2 is 10, which is obviously less than infinity. So we'll replace this infinity with 10. And the cost to travel from node S to node 6 is 24. So we'll replace this infinity by 24. And the cost to expand from S to node 7 is 12. So we'll replace this infinity with 12. All right, so now we have 10, you have 24, you have 12. So now what we are going to do is we'll expand the node which has the least cost or the lowermost cost. Like out of all these nodes, 10, 24, 12, infinity, 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 node 2 has the least cost, right? So if I expand node 2 in along all its neighbors, node 2 only has one neighbor, that is node 3. And the cost to move from node 2 to node 3 is 24. So total cost, I'll replace this infinity with 24, like so. So like we have expanded all the neighbors of node 2, like so. So we'll exclude node 2 from further exploration. Yes. And now what next? Now what are the nodes yet to be explored? We have 24. Sorry, we have 24. We have 24 here as well. We have 12 here, and everywhere else it is infinity. So the next least cost is actually node 7, which has a cost of 12. So we'll explore all the neighbors of node 7, which is node 6, node 5, and node T, right? So node 7 to node 6 is 12 plus this 5 units, which is 17. That is less than 24. So we'll replace this 24 with 17, right? Then we'll expand node 7 along node 5. That is 12 plus 13. That is 25, which is less than infinity. So that becomes 25. Then we'll explore node 7 along node T. That is 44. So 44 plus 12. So that becomes 56. So I'll replace this infinity with 56. All right. So I believe we have explored all the nodes from node 7. So we'll also exclude node 7 from further exploration. Node 7. All right. Now, which node has the least cost? Which node has the least cost? I think I probably might have made a mistake. This is not 24. This is supposed to be, we expanded it from node 2, right? So this is 10 plus 24, that is 34 actually. Now we see the nodes which has the least cost, that is node 6, right? Now we expand all the neighbors of node 6. So if you expand along node 3, that is 17 plus 18, that is 25, right? Uh, 17 plus 18, that is 35, sorry. 17, already it has 17, now it has to go 18, so it has 35. So 35 is actually higher than 34, so we'll keep the lowermost cost, that is 34 itself, right? So we'll keep 34 itself. Then if we expand 6 along 5, it should be 17 plus 21. That is obviously going to be higher than 25. So we'll keep 25 as such. Then we try to expand 6 along 7. So that is 17 plus 5, that is 21. That is also higher than 12. So we'll keep 12 as such. So I think we have explored all the possible nodes of node 6 as well. So like I'll remove node 6 from further exploration. Now, what are the other nodes? Now the smallest node is actually node 5 with a cost of 25. Everything else has a higher cost. So we'll expand node 5 along its neighbors. So node 5 along node 3 is 25 plus 2, that is 27. That is less than 34. So we'll replace this 34 with 27, right? So this path has already been explored. Then the other neighbor is 5 along 4. So that is 25 plus 15, that is 40, which is less than infinity. So I'll replace this infinity with 40. Then I'll explore 5 along node T. So that is 25 plus 18. That is 43. That is less than 56, right? So I'll replace 56 by 43, right? So I have explored this one. I have explored along this. I have explored along this. What if I explore along 7? So 25 plus 13, that is obviously going to be more than 12. And if I expand along 6, 25 plus 21, that is also going to be more than 70. So I believe I have explored all the nodes, all the neighbors of node 5 as well. So up to here, I have explored everything. I have visited all the nodes within this shaded portion. Now, what is the lowermost cost? Now, the lowermost cost is this one, node 3, with the cost of 27. So if I expand 27 along its neighbors, so 27, so expanding node 3 along node 4, that is 27 plus 6, that is going to be 33. That is less than 40. So I'll replace this 40 with 33. Expanding node 3 along node T, that is 27 plus 19, that is 37, 46. That is higher, higher than 43. So I'll preserve 43 itself, right? So any other combination that is actually uh, going to be higher. So we'll preserve everything. All right. So I believe we have explored all the neighboring nodes of node 3 as well. So I'll just exclude node 3 from further exploration as well. So node 3 is also excluded. Now we have node 4 remaining. So node 4, if I expand node 4 along node T in this direction, that will be 33 plus 21, that is 54. That is obviously higher than 43. So I'll just preserve 43 as such. And any other direction, if I try to explore, it is going to be more than the default value. So I think there is nothing much to be explored in node 4 as well. So that is also completely covered. Node 4 is also fully explored. So yeah, now we have actually explored all the nodes. We reached the only remaining node that is explored to be node T. So there is nothing much to be explored. The cost function won't be changing much. Cost function won't be changing at all. So the final cost function is actually 43 for the goal position. Now we have to backtrack and see, which path or which combination of path would give you this cost function of 43, right? So I believe it is, uh, what was it? 18 plus 13, that is uh, 31 plus 12, 41, 42, 43. I think it is this path that gives you 43, right? So the path S75T would give you 12 plus 13 plus 18. This is 43. Because 43 is actually the final cost that you have estimated for the goal position. So your answer, the shortest path from S to T is given by this cost 43. That is indeed S25 and T. I think the correct option would be S2, S75T is option E, the final option. That is indeed the correct answer. Moving on to question 8, this is basically a definition of what you have seen. The algorithm expands the nodes starting from the start similar to the breadth first search, except the neighbors are expanded. Neighbors of the expanded node are placed in a heap and reordered according to their value, which corresponds to the cost. Subsequently, the cheapest state on the heap, the top of the element after reordering, is extracted and expanded. This process continues until the goal node is expanded or no more nodes remain on the heap. A solution can then be backtracked from the goal to start. This is exactly what we did in the previous question, right? So this is basically a description of what we did in the previous exam. And that corresponds to this Dijkstra's algorithm. So it is basically a description of what we have done in the previous step. So the correct answer is indeed Dijkstra's algorithm. Option. Sorry, I think it is Dijkstra's algorithm, right? Correct answer is option F, but it's given breadth first. It is indeed Dijkstra's algorithm. And moving on to question 9, which graph construction method matches with the following sentence? The robot paths comes as close as possible to obstacles and resulting optimal paths are minimum length solution. So like of all the graph search methods we have seen, this is a word by word definition of visibility graph. Whereas in Voronoi, it tries to make as far as possible. Then for question 9, answer is indeed visibility graph. And for the final question, choose the wrong statement. The first statement is Dijkstra algorithm is a special class of A-star algorithm where the heuristic cost is 0 for all nodes. That is indeed true. The second option is potential field path planning treats the robot as a point under the influence of artificial potential field. The goal acts as repulsive force. So goal is actually always attractive. So that is also false. So the third statement is since Voronoi diagram graph represents a method maximizes the distance to the obstacles, any short range sensors on the robot will be in danger of failing to sense surroundings. That is true. And for this, in Buck2 algorithm, the obstacle fully circles the obstacle. That is false. It only fully circles the obstacle in Bug1. In Bug2, it tries to break away at the first line of sight to the next obstacle. So the wrong statements it appears that the wrong statements are option B and option D. Yeah, it only says option B, but both of these are actually wrong. So you should select these two answers. So that's it for this session. I have nothing more to add. All right, so thank you. I am ending this session right now. Okay, stop.